Hello and welcome to another class of ATMO 620. I hope you're all doing well. I hope you're enjoying this class. And I hope you're following along with the sort of the journey that we are taking through cloud microphysics, you might call it. So today we are going to talk about a very, very interesting topic, which is super important, maybe not necessarily super important for Hawaii, given the type of convection and convective clouds that we get here, but it is very important for atmospheric sciences and to understand clouds and rain and precipitation in general everywhere. I'm talking, of course, about ice. I don't know if you've ever thought of this, and probably you've seen this in classes already, so it's no news to you, but, well, the air is cold above a certain altitude, and the clouds that can reach to great altitudes, way past the sort of the freezing line in the mid-troposphere, these clouds above the freezing line start to be made of ice crystals. And this is regardless of where you are and regardless of how precipitation eventually even just falls on the ground. And so even if you are in the deep tropics, in the ITCZ, right? Very near the equator, where temperatures at the surface are really, really high, about 30 Celsius degrees, and it's hot and whatnot. High above in the atmosphere, it's still very cold, and as a result, the thunderclouds that make those storms that are part of the ITCZ are made of ice. And so understanding ice is crucial to understand convection in general, not just convection in really, really cold areas like the Arctic or for things like synoptic systems that affect the mid-latitudes like nor'easter storms on the East Coast and whatnot. And so ice is very important. And also, I think one reason why it's important to talk about ice is that I think, in my opinion, but also I would say almost objectively, ice is incredibly more complicated than liquid water to study and to understand. And so ice is still ice crystals and the formation of snow and hail, for example, and graupel that are all forms of precipitation that involve the solid phase of water. These are still subject of very active research because we understand ice very, very little. And I find this very interesting because ice is such a mundane thing, right? We all have experience with ice. It's what we ski on. It's what we put in our drinks. And in spite of this mundanity, in spite of this, that's even a word, in spite of this, in spite of the fact that ice is so common even within our lives, it is so hard to understand. So why don't we start talking about ice and ice in the atmosphere? First of all, what is ice? Well, ice, this again, I'm assuming you'll know the answer to this question to some extent. Ice is the solid phase of water, okay? Of what we call water. Of the water substance. And it's in this phase, when you are at temperatures between 0 Celsius degrees and minus 80 Celsius degrees, and at pressure that is similar, that is pressure at pressures that are within the range that is achieved on Earth, then water crystallizes, okay? pretty much naturally. We'll see how natural and how spontaneous this process is. But once the process starts, then the crystallization continues. What is interesting is that the water molecule has different ways, and I think this is probably what makes ice such a complicated thing to study. The water molecule has different ways to crystallize, different ways to form the crystal. In general, each water molecule is always surrounded by, each oxygen atom in ice is surrounded by 4 neighbor oxygen atoms, okay? And there's a distance in this crystal that is roughly between 20 and 30 nanometers, okay? When you form these tetrahedra, where the vertices are the oxygen atoms, so these tetrahedra of oxygen atoms, you then have multiple ways to combine these tetrahedra, okay? And these, in turn, give rise to different types of ice. And this is something that maybe you've never realized or you've never noticed, but ice looks different according to the temperature and the pressure at which it forms, okay? And this is not something that is typical of water only. Other things have different ways of combining, of crystallizing, if you will. So if you take carbon, for example, carbon has different ways to crystallize. There's one way in which you'd have, I believe they are sort of sheets of hexagons. Okay, so these are, no, that's wrong. Sorry. Hexagons of, boy, that was large. These are all carbon atoms. I'm citing this from memory, so the details might be slightly different, but it goes more or less like this, where you have sheets of carbon atoms that are sort of weakly coupled with each other. You know, they kind of weakly attract each other, something like this. And you have a structure that is made of these sheets of almost honeycomb carbon atoms. And this is what we call graphite, and it's what makes pencils, right? Whenever you write, one of these sheets gets transferred to the paper and it kind of sticks there. But this is not the only way that carbon atoms can form a crystal. Another way is at particularly high pressure, instead of having hexagons, carbon atoms can form, I believe they're again tetrahedra, if I'm not mistaken. And these tetrahedra are kind of strongly, all the atoms are sort of strongly bound together, and these tetrahedra are packed together. And what you end up having is a diamond, okay? So even the same substance, even something as simple as carbon, has different ways of forming a solid, okay? And with ice, it's exactly the same thing, okay? This plot here, so the plot before just showed you kind of some kind of illustrations just to give you an idea of what you might have. And this plot here shows all the different phases of, or some of the different phases of ice together with liquid and vapor, right? So here you have temperature on the x-axis and you have pressure on the y-axis. Atmospheric conditions are, somewhere between minus 100, I would say, more or less, minus 60, up to probably 30 degrees. And in terms of pressure, we would be, these are kilopascals, not hectopascals. So we would be about, at the surface would be at 100 kilopascals, and then going up, this would kind of decrease, and 10 pascals, I believe this would be in the stratosphere, okay? And so this would be sort of the range of interest for us, right? And the kinds of ice crystals that are formed. This IH is what we would have in our fridge and in the atmosphere. But this is not the only way that ice crystals can be formed. Okay, so for example, if you decrease the temperature below minus 100 degrees, then you'd have another phase. And if you go even further down below minus 200 degrees, then you'd have another phase altogether. The other phases, as you can see, are reached at really, really high pressures. And none of these exist, as far as I'm aware, exist naturally on Earth. Okay? You can still recreate them in the lab where these things have been studied, but on Earth, not quite so simple. Okay, so just keep in mind that that ice is a little bit weird, and it's a little bit weird in the way that it forms, a solid. Okay, so let's start talking about the formation of ice crystals. Now, if you remember, when we talked about the formation of water droplets, we said that there was a way, when you reach really high supersaturation, there was a way to form water droplets just literally out of air and water vapor. Okay, and we call that homogeneous, sort of the homogeneous mode, if you will, for the formation of cloud droplets. Now, that was, if you remember, we said that was a very, very hard process to have in the atmosphere, because it required, due to the surface tension of water molecules, little water droplets, and given to the fact that water molecules don't naturally attract each other very strongly, it required a lot of supersaturation to form. Okay, something similar happens also in the atmosphere for ice, in that we also have a type of nucleation that is called homogeneous freezing, if you will. And you have homogeneous freezing whenever you are, first of all, at the right conditions of temperature and pressure, and then you have fluctuations in the water drop that make it such that a stable structure is created. What I mean by all this? Well, whenever you have a combination of a collection of water molecules, okay, these water molecules will have a particular configuration, okay? I don't know, I'm just drawing randomly. And this configuration will have some kind of an energy associated with it, okay? Much like if you are in your room, for example, you have an empty bookshelf, then I give you 3 books. You have many ways to arrange these books on your bookshelf. And different arrangements will be associated to different energy levels. Well, what does that mean? Well, in the case of the books, the higher you put the books, the the greater the potential energy will be, right? Potential energy goes like GH, where H is the height from the ground. And so the higher you put them, you'll have greater potential energy. And so, for example, if you perturb your system bookshelf a little bit, so if you shake it a bit, books will tend to, this system will tend to flow to a lower energy configuration, i.e. the books will fall, okay? But if you put the books in the bottom shelf, then you shake them a little bit, but they're already close to the ground, so they're not going to fall out. Okay, they're not going to fall lower than that. Well, something similar can happen in this case, right? So if you have all the molecules, for example, if you were to put them all together, very, very close together, then these, if you remember, we said these would kind of repel at first, okay? And so this configuration would have a really, really high energy, okay? If you take them apart, they will have low energy because they don't really repel each other anymore, okay? And so each configuration has a particular kind of energy associated with it. And it may happen that when the conditions are ripe, some energy configurations are at a lower level than others, okay? And so when you are at sub-freezing conditions, the configuration where, these water molecules are, they take the shape of a tetrahedron, for example, maybe this has a lower energy that the configuration where all these are just randomly distributed. And if this is a lower energy, then once the molecules assume these positions, then they'll kind of stick there, right? The books that fall when you shake the bookshelf, they're not going to jump back up, right? If you keep shaking. Once you've reached a configuration that is a minimum or even a relative minimum of your stability, of your energy, then you tend to stay there, right? Unless you provide energy to the system, or unless you perturb it or destroy it in some form. So something similar happens to water droplets below freezing, okay? Now, this process obviously depends on a few things. First of all, the probability that something like this happens are kind of low, because molecules, remember, this is a liquid, so even though particles are not as free as in a gas, the molecules are kind of moving around in all directions. And so what happens usually is that there needs to be an ice nucleus around which these things should form. The ice embryo is what we call it. That is similar to the cloud condensation nuclei that we saw for liquid nucleation. In the case of homogeneous freezing, you don't have that, obviously, because we're assuming that we're in perfectly clean positions, perfectly clean conditions. And so the chance of something like this happening are, well, they're pretty low, first of all, because molecules are moving around. If you already have some kind of an ice nucleus that is formed out of pure chance, then it's easier to then grow something around it, right? Because suppose you have this ice nucleus that is formed, this will automatically try to convince other water molecules to take the positions that would allow this to grow even further, okay? And also, of course, this process depends on the probability that that the molecules will rearrange themselves, will find themselves exactly in that position that will help the formation of the ice nucleus. So, for this reason, homogeneous freezing is quite an unlikely process to happen at normal conditions, right? At 0 degrees Celsius, it's really unlikely that you'll form ice crystals just normally out of, pure sheer chance that molecules rearrange themselves in the right configuration. Homogeneous ice nucleation, or homogeneous freezing, a better word, will happen spontaneously at temperatures lower than minus 40 degrees, which is really cold, okay? And so only at really, really high altitudes does homogeneous freezing happens naturally. So again, this is interesting because it suggests that what we consider sort of natural processes to happen actually quite rarely in the atmosphere, and you always need something else to make them happen, some kind of catalyst. What is not uncommon to find is what we call supercool liquid water droplets at temperatures, as low as minus 20 degrees. These are water droplets, bona fide water droplets that are at really, really cold temperatures the molecules within the water droplets will have slowed down. Remember, temperature is associated with the kinetic energy of the molecules. But still, they haven't slowed down enough to make the right configurations probable. And so you'd end up having these things that are just, water droplets at super cold temperatures. Now, what happens, and we'll see this when we talk about the formation of precipitation, what happens in these cases is that if you were to touch these molecules with a tiny little ice crystals, for example, these droplets will freeze immediately, okay, in almost no time. And the reason why that is that, if you were to zoom in the collision zone, here you'd have the surface of the liquid droplet, and here you'd have the ice crystal. And the ice crystal is made of, I'm not drawing this correctly, but is made of tetrahedra, okay? And the tetrahedra will normally want to attract other particles in these tetrahedral positions so that the crystal can grow, okay, when the conditions are right. And so once this touches the surface of the liquid droplet, then this will cause a rearrangement of the molecules in the liquid droplet. Okay, so another way that you could have these ice crystals or ice particles to form is by another process that we call deposition or homogeneous deposition. And this happens not when liquid freezes, but when vapor molecules directly, as the name suggests, deposit on the ice crystal. So this is the ice crystal with all the tetrahedra. So imagine these are all tetrahedra collected together. You have vapor molecules around, of course, right? These are molecules in vapor phase. Some of these, when the conditions are right, may attach to the tetrahedra and become part of the ice crystal itself. Now, this is something that can happen in the atmosphere, but it typically requires really, really high values of supersaturation. And notice that here it would be supersaturation with respect to ice, not with respect to water. So, and we generally indicate this with an SI. Okay, supersaturation with respect to ice. This mode of ice crystal production, of ice production, can be formed in a lab, but it's kind of hard to find in the real atmosphere. Okay, so so we have two modes to build ice crystals that we discussed so far. We have homogeneous nucleation of ice and vapor deposition or direct deposition. Both these two are quite uncommon in the atmosphere, okay? So this suggests that the most common way is, like for liquid water, heterogeneous freezing, okay? And this is what I want to discuss now. With heterogeneous freezing, basically you'd have some particle from outside that we call this ice nucleus. And it's indicated typically by IN. Okay, so CCN was cloud condensation nuclei, and this is IN now for the ice. And there are many ways in which ice nucleus can stimulate the production of ice crystals. The first one is that when you are saturated with respect to ice, you could have heterogeneous deposition. Okay, so you have your ice nucleus here, and this will naturally cause water vapor molecules to sort of attach themselves to the crystal and acquire the precise position to become part of the crystal and to help the crystal growth. So this is one. The other one is that you could have a condensation freezing mode. So you have this, which is more like a cloud condensation nucleus, because it causes condensation, and then the condensation is accompanied by freezing. Another way that you could have this is something similar to what I mentioned before. You could have contact freezing. Contact freezing is that the moment that this particle touches a supercool liquid water droplet, this water droplet freezes immediately. And again, it may be because you have almost like a chain reaction, right? You have your supercool liquid water. And the supercool liquid water, you could think of this in a metastable state. So if this was like an energy plot, right? Your energy could do something like, could have a behavior like this, right? Normally, you'd always want to achieve the minimum energy that you reach, right? And if you were in this position, infinitesimal perturbations will send you back in this position, okay? However, if you give enough energy to the system that you might be able to overcome this potential barrier, then this will drag you down to a different minimum of your energy for the system. And this is a similar idea. So the supercool liquid water is almost a metastable state. And when you touch it with some ice nucleus, okay, some particle, this will cause a rearrangement of the particles around this ice nucleus. And this rearrangement will cause other water molecules to rearrange themselves and so forth. And this will drag you out of this and bring you to a new minimum state, which is the formation of an ice crystal. Okay. And finally, the other mode that could happen is what we call immersion mode. This is a mode in which you have some liquid water molecule that entrains a particle, okay? And this particle will act as an ice crystal only when the conditions are right, okay? When the conditions are right, this will act as a catalyst, and it will cause liquid water molecules around it to kind of rearrange themselves and then form the ice crystal, okay? So these are all the different ways that heterogeneous freezing could happen. Now, what are these ice nuclei? Well, these ice nuclei are, you'd be surprised that there's very little known about ice nuclei, actually. It's hard to study them, and it's hard to sample them in the atmosphere. They have been studied extensively in the labs, for example, where you can create cloud chambers and essentially where you cool down the temperature within the chamber and you cause freezing to happen. And then with various methods, you can observe their behavior, but it's still not clear why certain materials are better than others at nucleating ice. Okay. Typically, one of the interesting features is that not all the ice nuclei act as ice nuclei. So, if you have an experiment and you have all these ice nuclei, only a tiny fraction activates below a certain temperature. So here, using the numbers in the textbook, only one particle in 10 million particles activates as an ice nucleus. Okay, So things are not as straightforward as they were for cloud condensation nuclei. Typically, it's clay materials that act as ice nuclei. Again, you don't need to learn exactly what they are. Just keep in mind clay material. So kaolinite, calcite, some of these are found naturally in the soil. Kaolinite is one of the main components of porcelain, for example. So these are still kind of commonly found ingredients. Okay. And it's been found, interestingly, that also bacteria in some kind of environments can act as ice nuclei. And this is interesting. This is interesting. It's led to speculations. It often leads to speculations about the potential role of bacteria in forming ice in general. And you probably heard speculations that there may be life in the atmosphere of Venus, and that life is exactly living in clouds and potentially acting as sort of condensation nuclei. But anyway, bacteria are not the main responsible for ice nuclei, but they could potentially contribute to that. So, this also let it be a lesson that you should not, why you shouldn't eat snowflakes that fall from the sky, because you never know what caused the snowflake to form, actually. So it might actually contain some weird bacteria that you may not want to ingest. Okay, so here I just wanted to show some numbers, just to give you an idea of what contributes to the formation of ice nuclei. These are different regions in the world. There's Tula and Greenland, Missouri, Michigan, and you see that here it's the number that is being counted, and this is the percentage. Out of 100 particles found in snow crystals, what is clay material, or what is product of combustion, what is a microorganism, and whatnot. And you see that almost everywhere the clay mineral is the principal component. See these two locations in Japan. Missouri is kind of an exception in this case, but otherwise, clay is sort of the main responsible for the formation of ice nuclei. Microorganisms, that would be the bacteria that we talked about, almost everywhere are kind of, irrelevant. Still, they could nucleate ice crystals, but they're not as important as other things. Okay. So let's start talk about the ice phase within clouds, and not just in the abstract sense. The picture that I'm showing here is the picture of cirrus clouds. That we spell this, in case you've never heard or seen this. These are high clouds that can be observed quite often, actually. If you live in the mid-latitudes, these happen quite often during winter, for example. Here in Hawaii, they're not very common usually, but sometimes they can happen, and we see them on our heads, traveling in the opposite direction to the low-level trade wind flow. These here in Hawaii, we get them because they come out of anvils of thunderstorms that are formed on the ITCZ to the south of us. But essentially, the reason why I brought this up is that these are high clouds, and they are entirely made of ice crystals. Okay. And they live really, really high in the atmosphere. These are also clouds that are formed from contrails, essentially. Okay. Okay. So ice crystals in clouds are interesting because much like there exist different phases of ice, so different ways that ice crystals can grow. All right, so different different crystal structures, if you will. There can also be different ways that the crystals grow. So within the same type of phase, the crystal can grow in different ways according to temperature, pressure, and whatnot. Okay, we call these ice habits, and we'll talk about them in a few slides. Obviously, ice crystals you'd form in the atmosphere at pretty high altitudes. So freezing temperatures are usually at about 4 to 5 kilometers, more or less. And so above that, temperatures would be between 0 and 10 degrees. And so still not quite conducive to the formation of ice. But when you go at temperatures colder than minus 20 degrees, then you're guaranteed to have clouds everywhere. Okay. When you are warmer than minus 5 Celsius degrees, it's unlikely that there is any clouds. Concentration of ice crystals obviously varies from cloud to cloud and from cloud type to cloud type, and it can go from 100 per liter to 0.01, so 100th per liter. The clouds that I'm showing here, cirrus clouds, are usually pretty rich in ice crystals. And so when we think about ice and ice microphysics, one of the key questions that we are interested in from the research standpoint is, why is it that there's such a discrepancy, sometimes, of a factor of 10,000 between the concentration of ice nuclei and the concentration of ice crystals? Okay, so what makes an ice nucleus activate? Okay, and this is really a non-trivial question in the study of clouds and in the study of the cold phase of clouds. Here I have a link that I will not play, but I encourage every one of you to click on this. What this shows is the formation of ice crystals by so-called quote-unquote secondary processes. One way that we discussed until now for ice crystals to form is very simply, not very simply, but kind of straightforwardly, you have some ice nucleus that has been activated by whatever reason, and this leads to the production of ice crystals. So this is quite linear, okay? And this is a primary mode of production, if you will, okay? Heterogeneous, homogeneous freezing, doesn't matter. There are, however, details that there are ways that could help the formation of ice by other processes, okay? For example, you could have the situation where you have a liquid water droplet and the liquid water droplet is freezing. Now, the way that the liquid water droplet freezes is from the outside to the inside. So if we magnify this is the water droplet. First, the outer shell freezes, okay? And then the inner shells begin to freeze. Now, what's the trick here? The trick is that ice, unlike other substances, water, unlike other substances, expand in volume when it becomes solid, okay? Ice is, so when you freeze something, ice usually occupies a bigger volume, and this is something that we're all familiar with, right? It's the reason why ice floats. Unfortunately for the Titanic, it's the reason why you can go ice skating or skiing, because when you apply pressure, so when you compress the ice, okay, you make it, essentially you reverse the process of freezing in a way. And so when you compress it, you melt some of the ice. And so if you're standing on it, you melt a little bit of ice. This creates a tiny layer of water that acts as a lubricant. And so you can ski or snow or do whatever. If you were to stand on a wooden table, now wood, I don't know what wood looks like when it's liquid, but it doesn't expand. Usually things lose volume when they become solid, when they go from liquid to solid. And so if you were to stand on wood, on a tree, on a table, whatever, by compressing it, you're making it really, really happy, because wood likes to be compressed when it's solid, when it turns solid. Okay, and that's why you cannot ski on your table, and that's why you can't ice skate on or ski down a bare mountain with no snow. Okay, this was a long digression to say what? Well, to say that you have the liquid water droplet, the outer layer freezes, and so this causes, I don't know why I draw terribly. I'm sorry. And so this freezes, and it forms sort of a hard shell, okay, around the liquid droplet. When these layers freeze, okay, this one expands a little bit when it freezes, but then it becomes hard, right, because you've turned solid. When the inner layer freezes, so when this layer freezes, it naturally wants to expand as well, but what happens is that it encounters the outer layer that has frozen already. And so it encounters a resistance. And so what usually happens, and what can happen and does happen in clouds, is that these droplets, when they freeze, they literally explode. They shatter. They break in half, or they shatter. And so from a liquid droplet that freezes, you end up having a piece that have, like shards that, because of the explosion, are thrown pretty much everywhere, right? Maybe this is a bit heavier, so it doesn't travel as far. Conservation of momentum. And what happens? Well, now these projectiles, when they hit, imagine that in the cloud you're surrounded by liquid water droplets. When these ice projectiles, hit one of these ice droplets, well, they will likely cause this liquid droplet to freeze, and this will then break in many shards, and they will all go, and so forth. This formation of ice is called secondary ice production. Okay. And it's still one big open question, because to not only to understand this process more deeply, but also to understand it at a quantitative level. Given an ice particle that freezes, when and for which conditions is this particle going to explode? If it's going to explode, in how many shards is it going to explode? What is their size, their weight, their direction, their velocity, and so forth. Quantifying all these things is really, really hard. Observing these processes in clouds is extremely hard. Okay, and so very little is known about secondary ice production in clouds. Okay, this says pretty much what I just said. But yeah, I encourage everyone to click on this link and check it out, because it's super cool. It's literally super cool. Like, the liquid droplets are super cool, and you'll see them when they freeze and they explode. Okay, so speaking about quantitatively, a quantitative estimation of processes. Now we will talk about the growth of ice crystals, okay, and how we can understand this process in a quantitative way. Um, the let's see. So remember that we talked about saturation in clouds with respect to liquid water, and we talked about the diffusive growth of liquid water particles once saturation with respect to water is achieved. Okay, and we call the saturation ratio E over ES, vapor pressure over saturation with respect to water. We call it S. The saturation with respect to ice is defined in a very similar way. And this is vapor pressure over the saturation vapor pressure with respect to ice. This can be rearranged, and the saturation ratio with respect to ice can be written as the saturation ratio with respect to water times the product of the saturation vapor pressure with respect to water and the saturation vapor pressure with respect to ice. The ratio between these two, this is shown as a supersaturation in percentage, is shown here. Okay. So at freezing temperatures, this is 0%, meaning that these two ES and EI are the same. But notice that at colder temperatures, you are saturated with respect to ice before you are supersaturated with respect to water. Okay. So a cloud that is water saturated typically has, when you're below freezing, typically is supersaturated with respect to ice. Okay. Okay. Now, when you want to study the diffusive growth of ice crystals, meaning how, you start with some ice crystal here, and how vapor molecules can attach and help this crystal to increase in shape, okay, to grow in shape. This is a very similar problem to what we saw for the liquid droplets, okay? Essentially, we assume that this is a diffusive process, and so the mass of the ice crystal grows, if you go back and look at the equation that we used, as 4 pi d, where d is some diffusivity factor, times the difference between the vapor next to the droplet and the vapor at a great distance, times a constant that we now call C. Okay. This constant is what we call a form factor. Okay. And this is definitely something different from the liquid water droplet. What is this, and why do we need it? Well, water, if you remember, I'm sure you're aware that water droplets have a quasi-spherical form. And if you are a vapor molecule, there's a spherical symmetry. Like, you could attach to this water droplet pretty much everywhere, and you'd be happy, and the droplet would be happy. But with the ice crystal, that's not always the case. Well, that's not the case because the crystal has a definite shape. And if you want to help the crystal growth, you have to align yourself in the right, you have to go in the right position to help the crystal grow. Okay. And so if you're, for example, let's say that these particles need to align in these two directions to help the crystal grow for whatever reason. We'll talk about. Excuse me. We'll talk about the shape of ice crystals in a couple of slides. But the point here is that if for whatever reason this ice crystal only wants to grow in this direction, okay, this dimension here, if you're a water vapor molecule and you want to attach yourself here, you're not going to be able to. Okay. And so this form factor kind of makes it does justice to this process. Okay. And it's a factor that depends on the shape of the crystal. So if you have a spherical crystal, okay, I'm not sure these exist, but if you have a spherical crystal, then this form factor is just a radius. Okay, and this is exactly the 4 pi r that we had for the liquid water droplet. If you have a circular disk, okay, so if you have a disk like this, then well, this goes like 2r over pi. If you have an ice needle, I'm not good at drawing ice needles, but good enough. Then it's a form like this, where A and B are essentially the what's the word I'm looking for? Well, you could think of them as the length scale in these two directions. Okay, so you could have an ice needle like this. Your ice needle, for whatever reason, could also be like really wide, but small, but thin, something like that. So what do these ice crystals look like? Well, these are pictures. These are images obtained with an electronic microscope. And these show some types of ice crystals that have formed at different temperatures. Okay. This is what we would call ice needles. Okay, these are various ice needles. This has a weird shape that I'm not even sure how to call, but it's like a square. These look more like snowflakes. Okay, and this is an interesting shape because it looks like, and it is probably a combination of two different growing modes, right? It looks like this guy here started growing as an ice needle, but then changed its mind and started growing like two different plates. And this is something that can happen, and which makes writing down the math of ice growth within clouds so complicated. Okay, because you may be we'll talk about this in a little bit, but yeah. So these are typical shapes that you can have. All right, so very complex shapes. You can idealize them to some extent, but yeah, it does make a difference. You could say that this is actually just some kind of a spheroid that looks like this. And everything, to some approximation, everything, is a spheroid. But, a spheroid has very different aerodynamics and very different properties than an ice crystal that looks like that, right? So be mindful of all these differences. And something similar to what we said about the growth of cloud liquid droplets applies to ice crystals. So you remember, we said, when the water vapor molecules attach to the liquid water droplet, they release some latent heat, right? Some latent heat of the word escapes me, but of condensation, of course, yeah. And so, you could write down the Kelvin relationships and whatnot. And at the end, we obtain, in this case, we would have latent heat by sublimation, not by condensation, right? Vapor goes directly into a solid phase, so that process is known as sublimation. And we obtain a formula that is very similar to what we had before for liquid water, with some changes. So in this case, it's the supersaturation with respect to ice. This is saturation vapor pressure with respect to ice. This is latent heat of sublimation, and so forth. But it's essentially a very similar equation to the one that we had seen before. Okay. Now, of course, as we said earlier, water vapor molecules must have the right size in order to be attached to in order to be attached to the ice crystal. And so the actual growth rate may be even lower than what we obtain here. Okay, so be mindful of the approximations that we used here. Okay, and so what I wanted to say about habits, ice crystal habits. Ice crystals that form at different temperatures and different humidity conditions have different shapes. Okay, this is a very approximate. Table, but it kind of helps us understand what's going on. And for example, for temperatures between -10 and -20, you could have lower humidities, you'd have solid plates. At higher humidities, you have dendrites. If the temperatures warm up a little, you can have prisms, for example, or ice needles. And so, if we go back to something like this looks like maybe there was a warmer temperature, and it formed an ice needle. But then temperature got colder, and the ice crystal decided that it wanted to grow as an ice crystal instead. And so what happens, you may be asking, yeah, but how much are conditions changing within the atmosphere? If you have a point at 7 kilometers, which is at -15 Celsius degrees, how can it go to -5 Celsius degrees? Well, the points in the atmosphere might not change by 10 degrees, but remember, the clouds are turbulent. And clouds are made of updrafts, right, and downdrafts. And so ice crystals go up and down in clouds. If you imagine a cumulonimbus cloud, right, this is the anvil. This, may be something like 1 kilometer, and this is 15 kilometers. Ice, ice begins to form here, more or less, and here you have the updraft that is going up, right, forming the cloud. As the ice particles go up, as the water vapor goes up, you might have some heterogeneous freezing going on here, and maybe that's exactly what happens, that here you start to create prisms, but then you go up here and you grow plates, for example. And, this then starts to fall, and maybe on the plates you'll start to grow ice needles again or whatever. If this is a summer thunderstorm, then it doesn't really matter for precipitation at the surface, because it's all going to melt below 1 kilometer. But it may actually make a difference. If you're trying to understand this cloud, it may make a difference what kind of ice crystal you're dealing with. It may make a difference if, instead of being a summer thunderstorm, this is a snowstorm that's going to affect your area, right? So you kind of need to be mindful of all the different habits of ice crystals. And mind you, here we're still talking about ice crystals. We're not talking about snow yet, right? So I know that I talked about precipitation, but just think of this only as the equivalent of cloud liquid droplets, okay? Not raindrops yet, or in this case, snow. Okay, so let me drink a little bit. Excuse me. Okay, so I apologize if I drink once in a while, but it's been super dry in these days, and so anyway, now ice crystals certainly may grow by deposition of water vapor, so by diffusion, but there are other ways that ice crystals can grow. One mode of growth is called accretion, and this happens when essentially you have an ice crystal that is precipitating, Okay, this we talked about earlier. And it encounters and it hits upon a super cool liquid water droplet. The ice crystal will typically be, excuse me, let me redraw this. The ice crystal will typically be a lot bigger, and it will encounter a small liquid water droplet, super cool liquid water droplet. What ends up happening is that this freezes upon contact and it stays attached to this. When many of these processes happen, you could imagine that this will then cause a growth of the ice crystal, right? It's not, depending on the turbulent structure or depending on what's going on in the cloud, the freezing may be instantaneous, in which case these just stick here, or it may not be instantaneous, in which case you'd have sort of denser structures than go forming, which is what happens when hail forms. We'll talk about hail in our next lecture. Okay. And accretion is presumably what happens for this ice crystal here. Okay. But you could also have a situation where this ice crystal comes across another ice crystal, and the two, when they collide, they kind of stick together. And this process, known as aggregation, is what happens, for example, when you begin to form snowflakes. Okay, it's what leads to the formation of snowflakes. Is there a way to quantify these growing modes, these modes of growth? This is kind of hard because, as you can imagine, the shape of these ice crystals is incredibly complex. And so it's hard to derive simple calculations. Remember that at the beginning of the class, I suggested that you look at the, I suggested as a textbook also the Cloud Microphysics textbook by Prupacker and Klett. There you can find more rigorous treatments of this process and how this process could be treated. But essentially, people often resumes to empirical formula. Okay. They have to use empirical formula because, for example, even for something as simple as computing the fall speed, right? Remember when we talked about collision and coalescence of liquid water droplets, which is kind of similar idea as the accretion process here, right? Where you have, in this case, you'd have an ice crystal that's falling and a liquid water droplet that's falling. Before, we had two liquid water droplets falling down. For these guys, it was kind of easier to estimate the fall speed because, well, these are perfect spheres, and so, well, we assumed they're perfect spheres, and so it's kind of easier. Ice crystals, however, they could be dendrites, they could be plates, they could be needles, they could be prisms, they could be hollow prisms, they could be full prisms, and whatnot. And each one of these habits has different fall velocities. Deriving a closed formula is extremely complicated. It may actually not even be possible. Okay, and that is why we use just a very simple empirical formula. How do we derive these formula? Well, the simplest way to do it is to create the right conditions to have, for example, suppose you want plates. Create these conditions in your lab and then measure with some kind of an optical tracking, measure the fall speed of these crystals for crystals of different diameters, and you end up having, all these various scatter plots. These are scatter plots because, again, the ice crystal, the plate can have different orientations, right? Suppose if it falls like this vertically, seen from above, it would look something like this. Then this would have a certain kind of aerodynamic resistance. Okay, if it were to fall flat, so seen from above, it would look like this. This would have a much different resistance to the flow. Okay, And the truth is that these ice crystals probably don't fall one way or another, but they probably just keep oscillating as they fall. So that's why you have all these different scatter points. And at the end of the day, you just draw some kind of a best fit, and you obtain a formula like this one. Okay. And so when you want to compute things like the way we did with collision coalescence, then you have to use empirical formula, because there's no simple way to obtain, for example, the fall speed velocity of the ice crystals. Even the mass of the ice crystal is not easy to determine, and it's usually just, again, through a best fit, it's related to the crystal diameter with some empirical formula. Having said that, we can use similar formula to what we used for the cloud, for collision and coalescence processes. If you remember, this is very similar to what we used. This is where you would want to use these empirical formula depending on what habit you want to consider. And probably, unless you know exactly what's going on in your cloud, or unless you have a very, very thin cloud, like cirrus clouds that, may be like 50 meters thick, and so they're only made of one type of crystal, you probably have to sum over all the possible ice crystal habits when you want to compute growth by accretion, okay? And this is a similar formula to what we had. This would be the radius of the ice crystal, fall velocity. This is the cloud liquid content of the cloud, and this is the mean collection efficiency. Okay, you can estimate empirically or with some assumptions. Okay. Something similar can be done with the aggregation process. Similar formula can be derived for the aggregation process. Now, there are many complications to this, because the collision is not as straightforward as you would possibly, as you would imagine. Collision between two liquid droplets, it's kind of easy because, these are spheres, and so no matter how you turn them around, they're always going to look like spheres. With ice crystals, if you have, a plate that has the shape, and, with another, let's draw it like this. Let's say there are two plates that are kind of overtaking each other. The probability for these two to collide and aggregate is, one quantity. But if one of these two was flipped, so instead of having that you had, a flat disk that was falling, then it would have a different probability of hitting the first crystal. Okay, so it's highly non-trivial, and it's the reason why we're only dedicating one lecture to this. But ice microphysics is still a very rich research area, and kind of still very complicated. Now, as we said, aggregation and accretion must take place often take place in the ice form, and they can cause the formation of great hydrometeors that, when they fall, they then create, they can be snowflakes, or they can be liquid water drops. One interesting thing is that often the water droplets that are observed at the surface, sometimes they're really, really small. It's almost like very light drizzle. If you do some calculation, you find that these are actually too small to be formed out of collision between, or accretion or aggregation between different ice crystals. And so often it's really just unaggregated ice crystals that are falling. They then melt and then give rise to the drizzle that you often find at the surface. Now, one interesting thing is that right now we've discussed ice and water as kind of two distinct things, sort of cold clouds and warm clouds. But in many types of clouds, like thunder clouds, for example, or thunderstorm clouds, these two phases kind of happen together at the same time. So in this case, we talk about mixed phase clouds, and in mixed phase clouds, everything literally can happen. So you'd have nucleation of liquid water at lower altitudes, but then you have freezing at greater altitudes, and it can be you can have direct deposition, you can have freezing of droplets that formed at lower altitudes, you can have heterogeneous freezing by contact mode, secondary ice production, and so forth. Interestingly, ice crystals grow very rapidly by diffusion, more rapidly than liquid water droplets. And so when you have cold clouds, then it is possible to form, to understand why precipitation forms pretty quickly after the formation of the cloud. Okay, this is pretty much what I wanted to say about ice clouds. I hope this was as clear as it could be. I hope it didn't confuse you. Ice is a very complicated topic, for better or worse, and I think it's a very fascinating topic because there are still so many questions about ice that we don't understand, but it's impossible to derive very sort of closed form mathematical formula for ice because it's just so complicated that either formula look really, really ugly, and you should never memorize them, and you should use them only when you need to use them, or the problem is even intractable because it's not possible to write down an explicit formula. Anyway, I hope this was clear. If you guys have any questions, as usual, please let me know, and I'll be more than happy to answer all your questions. Otherwise, I will see you next class. We'll talk about rain and snow.